The dawn of jet propulsion. The year was 1939. Across Europe, nations teetered on the brink of total war, and innovation became a matter of survival. Traditional propeller-driven aircraft had ruled the skies for decades. But a new concept was emerging: jet propulsion. Engineers and scientists in Germany and Britain raced against time, desperate to harness a technology that promised speed and performance far beyond anything previously imagined. In Germany, the Messerschmitt design office embarked on a daring project, the Me-262, the world's first operational jet fighter. Powered by the Jumo 004 turbojet engine, it could reach speeds approaching 540 miles per hour, leaving any Allied piston engine fighter far behind. The design was revolutionary, yet the engineering challenges were immense. Early jet engines suffered from extreme heat, rapid wear, and the constant threat of catastrophic failure. Each flight tested the limits of metallurgy and aerodynamics, pushing pilots and mechanics to their very edge. The Me-262 represented more than mere speed. Its operational ceiling and climb rate redefined tactical air combat. Formations of Allied bombers, once considered invulnerable at high altitude, could now be intercepted and destroyed before reaching their targets. The psychological impact was profound. News of jet fighters patrolling the skies spread quickly among Allied airmen. These were not just planes. They were harbingers of a new era in warfare, where technology could suddenly render conventional strategies obsolete. Across the English Channel, British engineers at Gloucester Aircraft and Rolls-Royce pursued their own jet projects. The Gloucester Meteor, powered by the Rolls-Royce Welland engine, became the first operational Allied jet fighter. Although the Meteor arrived too late to engage the Luftwaffe in large-scale combat, it demonstrated the Allies' capacity to innovate and adapt. This aircraft laid the groundwork for post-war aviation, influencing fighter designs for decades. Jet engines worked on a radically different principle than propeller aircraft. Instead of spinning blades to push air backward, they compressed incoming air, mixed it with fuel, ignited the mixture, and expelled it at high velocity. The resulting reaction propelled the aircraft forward. While the concept was simple, execution was anything but. Turbojet engines demanded precision machining, heat-resistant materials, and meticulously controlled fuel delivery. Mechanics and engineers had to maintain reliability in an environment where a single failure could be fatal. The Me-262's Jumo 004 engines produced approximately 1,980 pounds of thrust each, giving the aircraft an unprecedented top speed. Yet these engines were short-lived, often requiring replacement only after 25 flight hours. Pilots had to adjust to entirely new flight dynamics, higher speeds, different takeoff and landing procedures, and a unique balance that affected maneuvering and combat effectiveness. The combination of velocity, firepower, and aerodynamics created a platform capable of attacks that were previously impossible, changing the very nature of aerial combat. Beyond the mechanical marvel, jet technology had profound strategic implications. Military planners realized that speed alone could dictate the outcome of an air engagement. Jet aircraft could strike, evade, and retreat with a level of control unattainable by conventional fighters. Even a small number of operational jets could force entire enemy air forces to reconsider their tactics, reroute formations, and divert resources to counter this sudden threat. In Germany, the Me-262 was not merely a weapon. It was a symbol of technological superiority. Pilots described it as a machine that could rewrite the rules of aerial warfare. Its arrival on the front lines introduced a terrifying new variable for Allied bomber crews. These crews had relied on the relative predictability of piston engine fighters. Now, facing the Me-262, They confronted a foe that could appear and disappear at impossible speeds, striking before defense systems could react. The jet's arrival also accelerated innovation in pilot training, maintenance, and airfield infrastructure. Mechanics learned to service engines capable of reaching extreme temperatures. Flight instructors taught new tactics for high-speed engagements, and military logistics adapted to supply the specialized fuels and spare parts required by these revolutionary machines. Every detail mattered, and failure could cost lives instantly. While the Me-262 dominated headlines, British jets quietly prepared to enter combat. The Gloucester Meteor, although slower than its German counterpart, was a reliable, durable platform. It demonstrated that jet technology was not a fleeting advantage for Germany, but the future of aerial warfare worldwide. Engineers analyzed its design for lessons in fuel efficiency, aerodynamics, and engine reliability, laying the foundation for post-war aircraft development. By the summer of 1944, jet aircraft had begun altering the balance of power in the air. They demanded new strategies, forced innovations in anti-aircraft systems, and introduced the concept that speed and altitude could override traditional skill and numerical advantage. In many ways, the jet engine was not just an invention, it was a revolution, a technological leap that signaled the end of one era and the dawn of another. This was only the beginning. As jet propulsion reshaped the skies, engineers and pilots would push further, faster, and higher. The next decade would see the principles first tested in the crucible of war evolve into the foundations of modern aviation, marking the start of an era where human ambition and technological ingenuity would soar together into uncharted heights. Chapter 2: The V-2 Rocket, Germany's Revenge Weapon. While jet engines were revolutionizing the skies, another technological marvel was emerging on the ground, one that would change warfare forever. In the laboratories and test facilities of Peenemünde, Germany's top scientists were working on a weapon unlike anything the world had ever seen: the V-2 ballistic missile, officially designated as the Vergeltungswaffe II, or Revenge Weapon II. It represented the culmination of decades of rocketry research, primarily led by the brilliant yet controversial Wernher von Braun and his team. The V-2 was a masterpiece of engineering and ingenuity, a rocket that could travel over 200 miles and deliver a 1-ton warhead with pinpoint accuracy. Unlike conventional artillery, which relied on trajectory and line of sight, the V-2 traveled above the atmosphere, descending at supersonic speeds to strike its target. It was effectively unstoppable. Once launched, there was no defense, no interception. For those on the ground in London, Antwerp, or Liège, the missile was invisible until it struck, leaving only destruction and terror in its wake. The technical challenges of the V-2 were immense. The rocket measured over 14 meters in length and weighed more than 12,000 kilograms at launch. Its engine, burning a mixture of ethanol and liquid oxygen, produced 25 tons of thrust, propelling the missile to speeds exceeding 3,500 miles per hour. Engineers had to carefully calculate fuel ratios, guidance systems, and aerodynamics. A slight miscalculation could result in catastrophic failure, sending the missile back to the launch site in an explosion that could kill the crew and destroy the complex. Guidance was another remarkable achievement. The V-2 used a gyroscopic guidance system to maintain course, a complex network of sensors and mechanical computers that adjusted the rocket's fins during flight. Unlike conventional artillery, which could be aimed based on maps and measurement, the V-2 required engineers to translate distances, angles, and altitudes into precise mechanical instructions. Any error in calibration could mean the missile missing its target by miles. From the moment of ignition, the V-2 represented the future of warfare. It was the first human-made object to reach the edge of space, soaring above 100 kilometers before plunging back toward the Earth. For the first time, humans had created a weapon that traversed the boundaries of the atmosphere, a missile that would define modern rocketry and inspire future space exploration. The psychological impact of the V-2 was as significant as its physical destruction. Civilians in London awoke to sudden explosions, unaware of the missile's approach until the sound arrived. Unlike conventional bombings where warning sirens allowed for some preparation, the V-2 offered no such chance. Its supersonic descent meant there was only the deafening impact and fireball, a strike without warning, a symbol of the terror that modern technology could unleash. Behind the scenes, the production of the V-2 was a grim testament to human cost. Tens of thousands of forced laborers from across occupied Europe were conscripted to build these missiles in underground factories. Harsh conditions, starvation, and brutality claimed countless lives, with the V-2 success measured in both technological achievement and human suffering. Concentration camp prisoners were forced to assemble engines, weld hulls, and test components, enduring unimaginable conditions that left permanent scars. In combat, the V-2 was devastating. First deployed against London in September 1944, it struck without warning, collapsing buildings, destroying infrastructure, and killing thousands. Unlike conventional bombing raids, where there was no counterattack, no interception, and no effective civil defense, the missile's speed and trajectory made traditional anti-aircraft artillery useless. Radar could detect launch sites, but offered no means to stop the rocket mid-flight. Despite its destructive power, the V-2 had limitations. Each missile was expensive and resource-intensive, limiting the number Germany could deploy. Accuracy, while impressive for its time, was still variable. A significant percentage of rockets missed their intended targets. Launch preparation was complex, requiring specialized vehicles, fueling, and coordination. Yet even with these constraints, the V-2 forced the Allies to divert resources and attention to counter the new threat, demonstrating the strategic leverage of advanced technology. The V-2 also laid the groundwork for post-war rocketry and the space race. Wernher von Braun and many of his colleagues were captured by American forces in 1945, and their expertise became a cornerstone of the United States missile and space programs. The Saturn V rocket, which would carry humans to the moon, traced its lineage directly to the V-2. Similarly, the Soviet Union used captured V-2 technology and engineers to develop its own ballistic missile programs, establishing the foundations of the Cold War's arms race. The missile's legacy extended beyond military applications. It demonstrated that humanity could engineer vehicles capable of leaving the atmosphere and surviving extreme conditions. It also highlighted the ethical complexities of technological advancement. The V-2 was both a weapon of terror and a stepping stone to space exploration. The same principles that allowed it to strike cities with impunity also enabled satellites, intercontinental missiles, and human spaceflight. As the war drew to a close, the V-2 program became a race against time. Allied advances threatened launch sites, forcing German engineers to relocate facilities underground and disperse operations. Despite these setbacks, they continued launching missiles at London and Antwerp, maximizing their destructive potential, while Germany's defeat loomed inevitable. Each launch was a demonstration of both ingenuity and desperation, a final attempt to leverage technology in a conflict spiraling out of control. The combination of the V-2 and jet aircraft illustrated a profound shift in warfare. Speed, precision, and technological dominance were becoming decisive. Conventional forces could no longer rely solely on numbers or tradition. Innovation could dramatically alter the battlefield. For the first time, humans wielded tools capable of striking from above the clouds and beyond the atmosphere, reshaping strategy, defense, and the very nature of war itself. By the end of 1945, the world had witnessed the power of these innovations. Jet aircraft would soon dominate air forces globally, and ballistic missiles would evolve into instruments of both war and exploration. The V-2's design principles guided decades of aerospace engineering, while the ethical and strategic questions it raised continued to resonate. The missile represented a turning point, an era when human ingenuity began to reach beyond the skies and into space, forever changing our understanding of technology, power, and the cost of innovation.
Chapter 3: Jet Fighters in Combat, the Me-262 and Allied Response. By late 1944, the German Luftwaffe had begun deploying its first operational jet fighters into active combat zones. The Messerschmitt Me 262, the world's first operational jet-powered fighter, represented a technological leap that shocked Allied air forces. Pilots who had spent years mastering piston-engine aircraft were suddenly confronted with machines that could climb faster, accelerate quicker, and outpace any propeller-driven adversary. The impact on both strategy and morale was immediate and profound. The Me 262 was designed for speed and lethality. Equipped with two Jumo 004 turbojet engines, it could reach speeds exceeding 540 miles per hour, almost 100 miles per hour faster than the fastest Allied fighters. Its armament included four 30mm Mk-108 cannons, capable of tearing through bomber hulls with a few precise shots. The combination of speed, altitude advantage, and firepower made the Me 262 almost untouchable in traditional dogfights. German pilots learned to exploit these advantages meticulously. The Me 262's speed allowed them to conduct hit-and-run tactics, diving from high altitude to strike bomber formations, firing with devastating accuracy, and then using their speed to retreat before enemy fighters could respond. This approach minimized their exposure to Allied defensive fire while maximizing the destruction inflicted on bombers. However, the jet had its vulnerabilities. Its engines were delicate, prone to failure if throttled improperly or subjected to sudden maneuvers. Takeoff and landing were particularly hazardous, with early jets often crashing due to inexperienced pilots or poor runway conditions. Allied forces quickly identified these weaknesses, focusing attacks on airfields and intercepting Me 262s during vulnerable phases of flight. Despite this, the Me 262 maintained a fearsome reputation among Allied crews, becoming a symbol of the Luftwaffe's technological edge even as the Third Reich faced imminent defeat. The Allies responded with urgency. The Royal Air Force and United States Army Air Forces intensified jet research, understanding that speed would define the future of air combat. While operational jets would not arrive in large numbers until after the war, experiments with early British and American designs, like the Gloucester Meteor and Bell P-59 Aerocomet, provided critical experience in jet flight, tactics, and engine maintenance. These programs demonstrated the growing importance of pilot adaptation, engineering resilience, and rapid technological assimilation. In parallel, strategic bombing campaigns were adapted to account for the new threat. Formation tactics changed, with bombers flying tighter groups to concentrate defensive fire. Escort fighters were modified to intercept jets, employing high-speed maneuvers and coordinated attacks to exploit the Me 262's weaknesses during takeoff or landing. Intelligence operations prioritized gathering data on jet bases, engine performance, and aircraft capabilities, highlighting the role of information as a force multiplier in modern warfare. The psychological effect of the Me 262 extended beyond the battlefield. Allied airmen spoke of ghost jets appearing suddenly, attacking with incredible speed, and disappearing just as fast. Bomber crews, already facing anti-aircraft fire and long missions, had to contend with an altogether new threat that required split-second reactions and trust in defensive gunners. Reports of Me 262 encounters circulated widely, influencing strategy discussions and inspiring accelerated development of jet aircraft for post-war service. One notable engagement occurred in April 1945 over southern Germany. A flight of Me 262s intercepted Allied bomber formations approaching key industrial targets. Within minutes, the jets destroyed or damaged multiple bombers, forcing surviving aircraft to abort missions or scatter. Yet the Allies had learned from previous encounters. Escorting fighters coordinated attacks on the Me-262s as they attempted to disengage, successfully downing several jets. This clash illustrated the delicate balance between technological advantage and tactical ingenuity. Maintenance and logistics presented additional challenges for the Germans. The Jumo 004 engines, while revolutionary, had short operational lifespans and required constant attention. Spare parts were scarce, and Allied bombing of industrial centers further disrupted supply lines. Pilots often flew missions knowing that engine failure could occur at any moment. Despite these difficulties, the Me-262 remained a symbol of technological prowess and a formidable threat that required serious attention from Allied command. The experience of jet combat had broader implications for aviation doctrine. High-speed engagement demanded new approaches to aerial tactics, including energy management, rapid decision-making, and long-range targeting. Pilots had to adapt to unprecedented speeds, altered visibility, and the new physics of jet propulsion. Training programs evolved quickly, emphasizing simulation, practice flights, and scenario planning to ensure that crews could exploit speed without succumbing to the dangers inherent in early jet flight. Post-war analysis confirmed the Me-262's impact. While it could not reverse Germany's strategic decline, it set the standard for future fighter development. Jets became the backbone of air forces worldwide, with lessons learned in the final months of World War II influencing design, armament, and operational doctrine for decades. Engineers and pilots recognized that speed, when combined with precision firepower and tactical innovation, could decisively alter air superiority in both war and peace. The Me-262 also catalyzed advances in Allied jet technology. Captured aircraft and technical manuals were meticulously studied. Engineers re-engineered components, evaluated aerodynamics, and assessed engine performance. This knowledge directly contributed to the rapid deployment of Allied jets in the late 1940s and early 1950s, marking the transition from propeller-driven fighters to the jet age. The combination of German jet fighters and the V-2 missile ballistic exemplified a new paradigm in military technology. Germany's innovations forced the Allies to adapt, accelerating post-war research and laying the groundwork for the Cold War arms race. These developments demonstrated a fundamental principle: technological superiority, when applied strategically and tactically, could create a temporary but profound shift in the balance of power. As 1945 progressed, the influence of jet fighters extended beyond immediate combat. The lessons learned in maintenance, engine design, pilot training, and high-speed tactics informed broader aviation practices. Manufacturers applied these insights to civilian aviation, jet transport, and experimental aircraft. Military planners began envisioning long-range jet bombers and supersonic interceptors, anticipating a world in which speed, altitude, and advanced propulsion systems would dominate aerial combat and defense strategies. The final months of the war showcased both the potential and limitations of jet technology. While Me-262s inflicted significant losses on Allied forces, they could not alter the course of a conflict defined by overwhelming industrial capacity, numbers, and logistics. Yet their legacy endured, inspiring generations of engineers, pilots, and strategists who recognized that human ingenuity, when coupled with advanced technology, could achieve feats previously thought impossible. In the broader context of aviation history, the Me-262 symbolized a transition. Propeller-driven aircraft would soon become obsolete in combat roles, replaced by faster, higher-flying, and more lethal jets. The principles developed during this period, engine reliability, aerodynamic efficiency, weapons integration, and high-speed tactics, became foundational to modern air forces. The Me-262's presence in the skies was brief, but its impact reverberated for decades, shaping the future of aerial warfare. By the end of the war, the world had glimpsed the dawn of the jet age. Pilots, engineers, and military planners had learned that speed, innovation, and technological adaptation were as decisive as numbers, strategy, or morale. The Me-262, for all its limitations, had proven that the skies belonged not only to those who fought bravely, but also to those who dared to imagine and implement the impossible. Chapter 4: V-2 Operational Campaigns and Strategic Impact. By 1944, Germany's V-2 ballistic missile had moved from concept to deadly reality. The V-2, or Vergeltungswaffe 2, represented a breakthrough in rocketry. A supersonic, liquid-fueled missile capable of delivering a 1-ton warhead to targets hundreds of kilometers away. Unlike conventional artillery or bombs, the V-2 could strike without warning, and no defense existed to stop it. Its launch produced a distinct, terrifying sonic boom that heralded destruction long before the warhead hit its target. The missile's origins traced back to the brilliant and ambitious German engineer Wernher von Braun. Working at the Peenemünde Army Research Center, von Braun and his team pushed the boundaries of propulsion, guidance, and aerodynamics. They solved complex problems that had stymied earlier rocketry efforts, stabilizing a long, slender missile in flight, achieving liquid fuel combustion that could be sustained for over a minute, and designing rudimentary gyroscopic guidance systems capable of directing the missile to a distant city with unprecedented accuracy for the era. The V-2's operational deployment began in September 1944. Launch sites were constructed in the Netherlands, Belgium, and France, often under concealment from Allied reconnaissance. Each missile required days of preparation, complex fueling operations, and a mobile launch crew that could move and hide before detection. Once fired, the missile accelerated to speeds exceeding 3,500 kilometers per hour, reaching altitudes above 180 kilometers, briefly leaving the atmosphere before descending toward its target. London became the first major target for V-2 strikes. The missiles arrived without warning, rendering traditional air raid sirens and defenses useless. Civilians and military personnel alike were terrified by the unexplained explosions that appeared suddenly and without prior warning. Damage was catastrophic. Entire blocks were destroyed in seconds and casualties mounted. Hospitals, transportation hubs, and industrial facilities were primary targets. The psychological effect was as devastating as the physical destruction. Despite the V-2's fearsome reputation, the missile was not without limitations. Accuracy was imperfect, targeting relied on early gyroscopic systems that could deviate several kilometers from intended coordinates. Production was slow, complicated by Allied bombing of factories and transportation networks. Each missile was expensive in both materials and labor, often requiring thousands of man-hours and critical components like liquid oxygen and alcohol fuels that were in scarce supply as the war progressed. The V-2's introduction forced Allied commanders to rethink both strategic planning and civilian defense. London's air defense systems, designed for conventional bombers, could not intercept the missiles. Civilian defense shifted toward evacuation planning, emergency medical response, and rapid rebuilding. Intelligence services worked tirelessly to identify launch sites, often relying on reconnaissance aircraft, resistance networks, and intercepted communications to prevent further strikes. Von Braun's role extended beyond engineering. He coordinated production, testing, and operational deployment. His team adapted quickly to setbacks. When launch failures occurred, sometimes with missiles exploding on the pad, engineers revised propellant mixtures, reinforced structural components, and adjusted guidance systems. Each failure provided critical data, advancing the technology despite the ongoing war. The psychological impact of the V-2 cannot be overstated. Unlike aircraft attacks, which allowed for some preparation and potential interception, the missile arrived without warning, breaking the rhythm of daily life. Londoners reported sleepless nights, constant anxiety, and a pervasive sense of helplessness. German propaganda heralded the V-2 as the revenge weapon, emphasizing its speed and unstoppable nature, hoping to undermine Allied morale while boosting domestic confidence. Operationally, V-2 strikes were concentrated but did not achieve decisive military effect. While civilian casualties were high and infrastructure damage substantial, the missiles could not alter the broader strategic trajectory of the war. Germany's industrial base was collapsing under sustained bombing, the Red Army was advancing from the east, and Allied forces were pushing into Western Europe. The V-2 remained a technological marvel, but a strategic gamble. Despite these limitations, the V-2 program laid the foundation for modern rocketry. Captured missiles, components, and von Braun himself were brought to the United States under Operation Paperclip. American engineers studied every aspect of the design, from propulsion and fuel chemistry to guidance and aerodynamics. The knowledge gained directly influenced the development of the Redstone, Jupiter, and Saturn series of rockets, ultimately enabling the Apollo missions and the moon landing decades later. The Soviet Union also benefited from V-2 technology. Captured rockets and documentation accelerated Soviet missile programs, establishing the basis for the R-1 and R-2 ballistic missiles. The Cold War arms race, including intercontinental ballistic missile development, traced its roots directly to the lessons learned from the V-2 program. In addition to technical legacy, the V-2 reshaped military doctrine. The concept of high-speed, long-range precision strikes emerged as a new dimension of warfare. Commanders began to recognize the importance of rapid mobility, dispersal, and hardened infrastructure to counter weapons that could strike unpredictably. Defense planning evolved to account for missile threats, influencing air defense networks, early warning systems, and the later development of missile intercept technologies. Field operators and engineers faced extraordinary challenges. Launch crews had to transport massive rockets on mobile platforms, assemble them quickly, and fuel them under threat of Allied detection. Safety was precarious. Even minor errors could lead to catastrophic explosions. Training was rigorous and continuous, emphasizing precision and coordination. The V-2's deployment demanded a level of technical skill, discipline, and courage unprecedented in previous weapon systems. The operational impact of the V-2 culminated in a brief but intense campaign against Antwerp, London, and later Liège. Hundreds of missiles were launched in late 1944 and early 1945, creating destruction on an industrial and civilian scale. Yet in the grand scope of World War II, these efforts could not reverse Germany's defeat. Strategic overextension, depleted resources, and the overwhelming might of the Allied powers meant that even the most advanced weapon of its time could not change the outcome. In retrospect, the V-2 program demonstrated both the promise and peril of technological innovation in warfare. The weapon's speed, range, and destructive power were revolutionary, offering a glimpse of what the future of combat could entail. However, the program's logistical demands, production challenges, and limited strategic effect highlighted the need for careful integration of new technologies into broader operational planning. The human story of the V-2 is equally compelling. Engineers, technicians, and soldiers worked under immense pressure, often at great personal risk, to transform theoretical designs into functional weapons. Many endured grueling labor, shortages, and air raids, yet their dedication advanced the science of rocketry by decades. The legacy of these individuals, especially von Braun, would shape not only military history, but space exploration and modern aerospace engineering. Ultimately, the V-2 remains a symbol of innovation under duress. Its influence on missile development, aerospace technology, and military doctrine was profound, leaving a lasting imprint on both the immediate post-war period and the following century. The weapon that rained terror on cities became the foundation for the rockets that carried humans into space, demonstrating that even instruments of war can inadvertently seed human achievement and technological progress.
The day after the Bismarck Sea assault, the Allied command gathered to assess the operation. The destruction had been total. Japanese forces had lost thousands of troops, their convoy shattered, and their naval strategies thrown into disarray. But more importantly, the operation had demonstrated something revolutionary. A single, well-trained, properly modified squadron could dominate an entire convoy, far beyond what conventional tactics predicted. At the center of this innovation was Paul Pappy Gunn, the former airline pilot and Navy mechanic, had turned the B-25 Mitchell into something entirely new. A low-level, heavily armed, fast-striking weapon. It wasn't just brute firepower, it was calculated precision. Every modification had been designed to solve specific problems: suppress anti-aircraft fire, destroy key targets, and allow bombs to hit accurately at minimal altitude. Gunn's approach was iterative, practical, and fearless. He tested, adjusted, and implemented in real time, often under extreme conditions with lives on the line. Captain Robert Chott and Major Ed Lana briefed new pilots on what had worked in the Bismarck Sea. They emphasized timing, coordination, and trust in the modifications made to their aircraft. It wasn't just flying, it was choreography. The B-25s had to move as a single integrated unit, each strike synchronized to maximize destruction while minimizing risk. Gunn's forward-thinking approach had transformed the aircraft into instruments of strategic dominance. The risk, however, was ever present. Flying at treetop height left no room for error. One miscalculation could mean collision with the water, a premature detonation of a bomb, or exposure to concentrated anti-aircraft fire. Yet the crews, hardened by training and inspired by their victories, approached each mission with confidence. The combination of skill, preparation, and Gunn's modifications created an almost unstoppable force. The Bismarck Sea operation also highlighted the importance of adaptability. Japanese forces attempted to alter their tactics in response to the unprecedented threat, but they were reacting to a dynamic problem with rigid thinking. The commerce destroyers, by contrast, were flexible, able to adjust their attack patterns mid-run. Skip bombing runs, strafing angles, and synchronized attacks allowed the pilots to respond in real time to changing circumstances, a decisive advantage in any battle. Allied leadership noted another key takeaway: morale. The pilots and crews of the modified B-25s understood that their aircraft had been transformed into something greater than standard bombers. They felt empowered, capable of decisive action even against superior numbers. Confidence, built through relentless training and proven effectiveness in combat, became a force multiplier. Fear of failure was replaced with anticipation of victory. The Japanese, watching from retreating vessels and damaged formations, began to understand the scale of the threat. Future convoys would face these tactics at every turn, and traditional defensive strategies were no longer sufficient. The psychological impact of the commerce destroyers would continue to shape Japanese operational decisions, forcing them into a defensive posture long before physical attacks reached them. Meanwhile, Gunn continued to innovate. He experimented with additional armament placements, improved ammunition feed systems, and reinforced aircraft structures to handle recoil. Each enhancement was tested in the field, often during actual missions. There was no time for bureaucratic approvals or manuals. There was only the need to save lives and achieve objectives. The success of the Bismarck Sea assault proved the value of this approach beyond doubt. By mid-March 1943, the Southwest Pacific Theater had learned a powerful lesson. Innovation in warfare often comes from those willing to take calculated risks, to challenge convention, and to implement real-world solutions under pressure. Gunn's work, combined with the courage of pilots like Chott and Lana, had established a template for future operations. The commerce destroyers were not just a technological modification. They represented a philosophy of combat, one where ingenuity and daring outweighed rigid adherence to doctrine. The legacy of Bismarck Sea would be felt for the remainder of the war. Every subsequent low-level bombing run, every coordinated strafing attack, and every skip bombing mission drew directly from the lessons learned during those critical hours. Pappy Gunn's vision had redefined aerial strategy in the Pacific, demonstrating that resourcefulness, courage, and innovation could decisively alter the course of a campaign.
Chapter 6: Legacy and Post-War Impact. The end of World War II did not mark the end of the technological revolutions born during the conflict. Jet engines, ballistic missiles, and experimental weaponry like the V-2 had created a new paradigm for warfare, aerospace, and even civilian industry. The innovations developed under the pressures of global conflict would continue to shape the post-war world in profound and lasting ways. Captured German scientists, engineers, and technology became the cornerstone of post-war aerospace development. In the United States, Operation Paperclip brought figures like Wernher von Braun and other leading rocketry experts into American military and space programs. Their knowledge directly influenced the Redstone, Jupiter, and Saturn rockets, which would eventually propel humans to the moon. Every design, calculation, and field modification learned in the crucible of wartime Germany contributed to what became the United States' strategic and technological advantage in the Cold War. Jet propulsion, too, transformed the aviation industry. The Allies' early jet fighters, developed to counter threats like the Messerschmitt Me 262, evolved into commercial airliners capable of transatlantic flight at unprecedented speeds. Military aviation entered a new era. The lessons of high-speed flight, jet engine reliability, and aerodynamics carried forward into the first generation of supersonic aircraft and beyond. These developments also influenced pilot training, maintenance protocols, and the design of aviation infrastructure such as longer runways and specialized hangars. The legacy of the V2 and similar technologies extended beyond military applications. Ballistic missile research, initially intended to deliver warheads, became the foundation for space exploration. The concept of multi-stage rockets, precise guidance systems, and high-thrust propulsion directly informed the development of satellite launch vehicles and crewed spacecraft. What was once a weapon of terror became the vehicle for human ambition to reach orbit and beyond. Strategically, the experience of the V2 and jet aircraft highlighted the importance of technological innovation in modern warfare. Military planners realized that traditional methods could be rendered obsolete almost overnight by breakthroughs in propulsion, guidance, or materials. Rapid prototyping, iterative testing, and adaptive tactics, practices honed under wartime necessity, became central to post-war defense planning and procurement. Nations now understood that technological edge could be decisive, sometimes more so than numerical superiority. The human cost of these innovations was significant. Forced labor, particularly in the construction of V2 launch sites like Peenemünde and Mittelwerk, left thousands dead or injured. Yet the engineers and pilots who survived the war carried forward a unique expertise. Their experiences, designing under pressure, solving unprecedented problems, and surviving extreme operational conditions, translated into post-war advances in aerospace engineering, industrial management, and scientific research. Internationally, the lessons of German technology sparked competition. The Soviet Union, aware of the United States' recruitment of German scientists and the capture of advanced equipment, accelerated its own missile and aerospace programs. This created the foundation for the Cold War arms race and the space race, with both superpowers seeking not just military dominance but also technological prestige. The ethical and moral dimensions of wartime innovation also became a subject of reflection. Technologies like the V2 demonstrated that scientific brilliance could be harnessed for destructive purposes. The post-war community of engineers and scientists grappled with the responsibilities of innovation. How to balance progress with safety, power with humanity, and ambition with ethical constraints. These debates would continue to influence both civilian and military research for decades. Beyond technology, World War II shaped institutional structures. Governments established permanent research and development agencies, such as the United States Jet Propulsion Laboratory and the Air Force's Wright-Patterson programs. Protocols for rapid deployment, field modification, and cross-disciplinary collaboration were formalized, ensuring that the wartime lessons in adaptation and innovation were institutionalized. The war also transformed industrial capacity. Factories capable of producing jet engines, rockets, and advanced armaments were repurposed for civilian production. The skills developed by wartime engineers, technicians, and laborers accelerated the post-war economy, driving innovation in aerospace, electronics, and manufacturing sectors. Civil aviation, space research, and even computer technology benefited from this transfer of knowledge. Finally, the psychological and cultural impact of wartime technology endured. Societies became aware of the transformative potential of science and engineering, both constructive and destructive. Popular imagination was captured by stories of rocket engineers, daring pilots, and audacious innovations that challenged the boundaries of what was thought possible. This legacy inspired generations of scientists, explorers, and military strategists to pursue bold, ambitious goals, often in areas that had been pioneered during the desperate years of global conflict. In conclusion, the legacy of jets, V-2 rockets, and wartime technological innovation is vast and multidimensional. It reshaped military doctrine, accelerated aerospace development, influenced global politics, and seeded the foundation for space exploration. The individuals who designed, built, and deployed these technologies, sometimes under morally complex conditions, left a mark that extended far beyond the battlefield. Their work demonstrated that innovation, even when born of necessity and destruction, could propel humanity into a new era of discovery and capability.